Air traffic management is entering a phase of fundamental and rapid changes in technology, airspace, and regulation. In the near future, not only will there be increasing use of automation across the aviation industry, but collaborative decision-making and strategic partnerships will also be critical in the delivery of an efficient and harmonized air traffic control system. As various technical systems and partnerships become more integrated, operational personnel and managers from many domains will need to work closely together in order to maintain and improve future safety. People involved in safety discussions need a shared understanding of fundamental safety principles. This film aims to provide a basic explanation for some of the key terminology and principles used in operational aviation risk management.
Let's start by making it clear what we mean by safety. It's a word that most people have an intuitive understanding of, but it helps to be precise. The International Civil Aviation Organization defines safety as the state in which the possibility of harm to persons or of property damage is reduced to and maintained at or below an acceptable level through a continuing process of hazard identification and safety risk management. Notice how this definition recognizes that the complete elimination of risk is impossible. All worthwhile human endeavors involve some possibility of harm. Safety is about managing that risk responsibly. Talking about acceptable possibilities of harm is rather abstract. So in order to communicate clearly about system vulnerabilities, we use the idea of hazards. The ICAO definition of a hazard is a condition or an object with the potential to cause injuries to personnel, damage to equipment or structures, loss of material, or reduction of ability to perform a prescribed function. The identification of hazards is crucial in safety management. Almost anything can be a hazard, but conceptually, hazards exist in the present. Hazard analysis is most useful when they are described at a level where they can be managed. For airport operations, a short runway or crossing runways could be a hazard. For a communications upgrade project, failure of a particular data link might be a hazard. A consequence, in contrast, is defined as the potential outcome or outcomes of a hazard. The damaging potential of a hazard arises through one or multiple consequences. The consequences of hazards occur in the future. Safety analysis should include the likely consequences of the hazards in practical terms without confusing hazards with their consequences. Of course, in an ideal world, all hazards would be eliminated. But in the real world, this is not always possible or practicable. Hazard identification and risk analysis allows us to communicate about risk and put in place appropriate technology, procedures, and training to control them. If a hazard cannot be eliminated, then our goal is to reduce the likelihood and severity of the consequences of the hazard. For any hazard, there may be a range of possible outcomes. For example, unintended simultaneous use of crossing runways is a potential consequence of crossing runways. The consequences range from a near miss to a catastrophic collision. Because there are a range of outcomes, each with a different likelihood and severity, we often choose one particular consequence to focus on. While the outcome could be an accident, an intermediate unsafe event may be identified as the worst credible outcome. Safety risk is a construct derived from the probability and severity scores for each consequence. The ICAO definition of safety risk is the projected likelihood and severity of the consequences or outcomes of a hazard. The safety risk of the worst credible outcome of the hazard can be assessed using probability and severity tables. There are many risk classification schemes available, and the scheme used needs to be optimized for the particular operational environment. Classification tables are used to provide common language for describing probability and severity. Words such as frequent or minor mean different things to different people, so the tables ground these terms with more complete descriptions. A risk matrix can be helpful for prioritizing decisions. Hazards with a high likelihood of catastrophic consequences deserve most attention. Hazards with low likelihood and low severity consequences warrant less effort. Classifications such as high, medium, or low are aids for decision-making with regard to the appropriate treatment for each hazard. The acronym ALARP is sometimes useful to describe a hazard with a safety risk that has been reduced to a level that is as low as reasonably practicable. Acceptability is determined not by the overall amount of risk, but by whether further risk reduction is practicable and not grossly outweighed by the cost. This may require a detailed cost-benefit analysis.
Apart from safety nets, what other means do we have available to prevent collisions from happening on crossing runways?
This is exactly what we were discussing last time. It's about the...
When the analysis indicates the safety risk of the consequence of a hazard is a LARP, this does not mean that the safety risk has been eliminated, only that the analysis indicates it has been brought under control. Some residual level of safety risk remains. However, the analysis indicates that the residual safety risk is sufficiently low that the cost of further risk reduction measures is outweighed by the benefits. The ICAO definition of an acceptable level of safety performance is the minimum level of safety performance of civil aviation in a state as defined in its state safety program, or of a service provider as defined in its safety management system expressed in terms of safety performance targets and safety performance indicators. The safety objectives for various operating environments are set by the national regulator. Classical risk mitigation is the process of incorporating defenses or preventive controls to lower the severity and/or likelihood of a hazard's projected consequences.
Swiss 1675, contact radar 128.
In risk management, the words mitigate and control have the same meaning. Traditionally, the main aviation safety defenses have been technology, training, and regulation. However, as system complexity increases, there are limits on the effectiveness of such controls. Flexibility and adaptation are essential for dealing with unanticipated events. Additional barriers or regulation increase complexity and reduce flexibility. Technology, especially automation, may mask underlying conditions, erode operator skills, or remove the means for effective intervention. New technology changes the work and opens new pathways to failure. Unintended consequences, including the introduction of new hazards, can result from the implementation of well-intended but misconceived risk mitigation measures. Even well-designed measures for safety improvement can be weakened as humans change their behavior in response to a perception of increased safety. This phenomenon is known as risk compensation. For these reasons, safety management is not just about identifying and controlling hazards, and this has become increasingly evident as the pace of technological development increases. The approach to safety risk management described so far is focused on reducing the number of things that go wrong and is sometimes referred to as Safety 1. Now let's look into the future. Many of the world's key international hub airports and ATM systems are reaching their capacity limits. At the same time, the need to reduce carbon emissions and other environmental impacts grows ever more urgent. Governments and companies around the world are therefore working to update their ATM systems. In Europe, the 6 pillars of the Single European Sky ATM Research Master Plan are moving from airspace to 4D trajectory management, traffic synchronization, network collaborative management, system-wide information management, airport integration and throughput, and conflict management and automation. The deployment baseline phase is already in place, and step 1, the transition to time-based operations, is now well underway. At the moment, controllers take almost total responsibility for the sequencing and separation of aircraft, and until recently many of their tools, such as paper strips and radio voice communications, were analog-based. However, the introduction of time-based operations, precision navigation, cockpit displays of traffic information, data links, automatic conflict detection, and automated sequencing tools mean that the ATM system is now gradually moving from analog systems and centralized human control to digital, semi-automatic and automatic systems and distributed decision-making. Information about the position of aircraft and their intentions, and a host of other information, will soon be fully exchangeable across a wide range of operational and supporting domains. Aircraft will fly continuous descent arrivals on data-linked 4D flight paths tailored to local constraints and timed for merging traffic. In the near future, air traffic management will rely on a collaborative decision-making approach. Air navigation service providers, airlines and airports will cooperate so that aircraft can fly optimal trajectories and to maximize the efficiency of ground handling and logistics. Critical choices will soon have to be made about the degree to which monitoring, analysis and control is handled by people or automation, and how trillions of bytes of information are filtered into manageable intelligence and displayed for use by people across many domains.
The implications of automation on safety are immense. They're far too large to be addressed in this film. But recent safety advances have shown that it depends not only on the absence of potentially harmful things, it relies on the presence of positive processes and behaviors. Resilience is especially crucial. Resilience is the intrinsic ability of a system to adjust its functioning prior to, during, or following changes and disturbances so that it can sustain required operations under both expected and unexpected conditions. So what are resilient systems? Well, first, they respond quickly and effectively to expected and unexpected conditions until control of the situation is restored. Second, they monitor their own performance and the environment to detect things which could or are causing changes or disturbances. And three, they learn from experiences, successes as well as failures. And four, they anticipate threats. They see developments and opportunities further into the future, like increased demand, potential changes, tighter constraints. So systems without these characteristics are brittle, and they may fail suddenly and catastrophically when disturbed. Now, people have shown that they have the flexibility, the adaptability, and the creativity necessary to deal with unanticipated events. They are a source of resilience. Resilient systems retain safety margins and reserves. Recent advances, they don't throw out safety one, but they show that it is incomplete. Identifying hazards, assessing risks, choosing appropriate controls, all of that is important, but real people in real organizations can't perform them perfectly continuously. Some hazards are never identified. Some controls are inappropriate, senseless for that level of risk, and some systems, they start off safe, but then they drift into dangerous states over time. Normal variability and unanticipated interactions in complex systems produce disturbances the whole time. These can magnify, cascade rapidly across the entire system. Catastrophic failures still occur even in the face of rigorous regulations, multiple safety barriers. Now, safety 1 means trying to reduce the number of things that go wrong. Safety 2 aims to ensure that as many things as possible go right. Safety 2 is proactive. It continuously tries to anticipate developments and events. Even in an organization that appears to be operating like clockwork, there's a lot of natural variation day to day. This is normal. It's desirable. Humans aren't robots, and in complex systems, we don't want them to be robots. It is exactly their adaptive capacity, their resilience, their flexibility that keeps things operating smoothly and helps return things to normal after they've gone wrong. Over time, though, an entire organization can shift its idea of what is normal. Small departures from routine rules and procedures can gradually build into larger shifts in beliefs and behavior. And according to most measures, things will be going well. Steps into danger may improve on-time performance, save money, increase customer satisfaction, but the operation may actually be sliding towards the margins. From inside an organization, drift is not obvious. You see, contrary to Murphy's Law, things which can go wrong often turn out okay, which teaches us the wrong lesson. Success can lead to this false confidence that we are doing things right. Rigid oversight processes, which rely on compliance audits, are really very poor mechanisms for the sort of control and feedback for real people. They can in fact perpetuate this false picture of how work is actually done, and it allows the system to drift into failure.
If Safety 1 methods alone cannot prevent drift into failure, what else do we need to do? A Safety 2 organization is interested in how normal work is done. Now, it doesn't ignore unusual incidents and safety problems, but it is equally concerned with the success stories, hiccups and frustrations of normal work. Safety 2 managers, they have an inquisitive mindset. They genuinely want to know about the work that is being performed and what makes it frustrating or difficult. Safety 2 managers, they listen. They're happy to learn new things from their staff, including better ways of performing the work. Safety 2 managers are less concerned with the written requirements for how work should be done, and more concerned with the safety, how it is actually done. Safety 2 managers know that having a genuine interest in understanding and improving people's working conditions is a better defense than just telling people to follow the rules and the procedures. Now, increased understanding won't come from just keeping operational people engaged with safety. Managers need to stay involved in normal operational work. Now, how do you apply Safety 2? We begin by not only asking questions about safety, but about people's work. What is the gap between written guidance and actual work? Why is the gap there? Now, the gap is not evidence of violations. Rather, it is evidence that an organization may be miscalibrated about how people have learned to cope with the messy details of real work. What does it take to get the job done on a daily basis? What are the workarounds, innovations, or improvisations that people have to engage in order to meet the various demands imposed on them? What are the daily frustrations that people encounter in getting a piece of machinery, or a technology, or even a team of people to work the way they expect. What do your people believe is dodgy about the operation? Ask them that question directly, and you may get some surprising results. What do people have to do to finish the design of the tools and technologies that the organization has given them to work with? Finishing the design may be obvious from little post-it notes with reminders for particular switches or settings, or more advanced jury-rigged solutions. Such finishing the design can be a marker of resilience. People adapt their tools and technologies to forestall or contain the risks that they know about. But it can also be a pointer to places where a system may be brittle. How often do people have to say to each other, "Here's how to make it work," when they discuss a particular technology or portion of the operations? What is the informal teaching and coaching that is going on in order to make that happen? To take responsibility for safety on the line, you should first and foremost look at people's work, more than just at people's safety.
You have seen in this video how managing safety in our rapidly evolving digital age requires more than simply creating additional safety barriers, audits, or safety compliance. System safety depends on controllers, pilots, technicians, designers, safety managers, operational managers, and multiple strategic partners working together to understand the messy detail of normal operational work. You will therefore understand how important your place is in these discussions and see that it is only by working together and understanding the system as a whole that we can all help to make our aviation system even safer in the future.